today's lesson we're going to be talking about forces. So in physics, we all kind of have an intuition about how objects move. So sometimes our beliefs are hard to change since they work well in our everyday lives. But there's limits in developing an understanding of how the world works, but we must build on that intuition to kind of move forward. So a good example of this is the Galileo versus Aristotle experience on how objects move. So in our experience, objects move, they must be pushed in order to keep them moving. So force would be needed to have a constant velocity, to keep an object moving at that constant velocity. So this is what Aristotle claimed when he first wrote his series of books entitled Physics, written about 2,400 years ago. About 400 years ago, though, Galileo, another scientist, proposed a different thought experiment to reveal another perspective on how objects move. So this is his thought experiment. So if you imagine two perfectly smooth ramps connected together by a perfectly smooth surface, if a ball was let go at the top of one ramp, so you can see the line here, what will happen when it gets to the other side? So if we let the ball roll, we notice that if the ball rolls down one ramp, it keeps rolling up the other side until it reaches the same height. Okay, so let's repeat this but make our second ramp a little bit less steep. What will happen? So our ball is starting here, marked by the line. So let's predict what's going to happen when it gets to the other side. Okay, so it's going to again keep rolling until it reaches that same height. It just has to roll further. So this is an interesting thought experiment. Now finally, let's make the ramp flat. What do we expect is going to happen now? So it's going to keep rolling forever. So there's no external force necessary to keep that ball in motion. And so it's not that Aristotle was wrong. So in our everyday lives, we do need to keep pushing an object to keep it moving. So we push it across a book across the table. When you stop pushing it, it stops moving. So Aristotle is right in terms of what we see around us in our everyday lives. It's just that Galileo and later Newton imagined a world without friction. So that ball would keep rolling forever because there's no friction. So there's no external force stopping it. And so you don't need to keep pushing it to keep it moving. So friction represents an external force acting on the object. So as you push, your push is an external force. Friction is pushing backwards on it. So in the absence of all external forces, an object's velocity is going to remain constant. So a good example is in outer space. There's no air resistance. So if you throw an object, it's going to keep moving at that constant speed in a straight line until it hits something else. So two equal and opposite forces have the same effect. They can cancel one another out. So what is a force? So I have a quick little video here going to be describing that. Or maybe not. So forces is half of an interaction. So it's a push or a pull. So half that interaction. The unit we use for force is a Newton, named after Isaac Newton. So it's a capital N for the symbol. And a lot of times we represent force with a vector. So force is directional, so it has a positive and negative direction. And so the arrow is going to tell you both the size of the force, so how big the arrow is tells you the bigger the force, and the arrow is going to point in the direction of the force. So we have a couple different groups of forces. So one kind of group are called applied forces. So it's a general term for any force in which you have to contact the object to apply it. So the symbol here for an applied force, so that force vector, we would label with the symbol what force it is. So if it's an applied force, we would write that symbol down next to the arrow. Other examples of applied forces are tension. So if you have something on a string or a rope or a cable, you would have a tension force, so the symbol for that would be F sub T, or sometimes we just write T for tension. Friction is an applied force, so the two surfaces have to come into contact to apply friction. So friction always opposes any attempted motion. So if we're moving to the right, our friction is to the left. If we're moving upwards, our friction is downwards. So it's always opposite your motion. So the symbol is F sub S, so force of friction. And then kind of one that people forget is normal force. So this acts on an object on a surface. So if you have a book on a table, gravity is obviously pulling the book downwards, right? It's not floating in air. But what keeps the book from falling through the table? So there has to be a force opposite gravity, and we call that the normal force because it's normally there, or normal as in perpendicular to a surface. So the normal force acts to keep objects apart from one another. Or any object on a surface or on the ground has a normal force pushing upwards. So we call that a normal force. So the symbol is F sub N for normal. So the other group of forces are ones where we don't need to have contact with the object to cause the force to be applied. So the big field force is a gravitational force. So F sub G, sometimes we write the equation which is mass times gravity, but the gravitational force is the force of attraction between all objects. So your weight is the gravitational force of Earth on you. So all we really are going to pay attention to in this lesson is the symbols, because we're going to be using those to draw some diagrams. So how do we show the forces acting on an object? And we call our drawings free body diagrams. So they're free from all other distractions in the situation. So free body diagrams can help us when we're trying to solve for forces acting on an object. So here's a quick video describing those.
What are the forces acting on you right now? I want to answer this question by introducing something called a free body diagram. This is a sketch that scientists make that shows all the forces acting on an object. Each force is represented by an arrow. The size of the arrow represents the magnitude of the force, and its direction indicates the direction of the force. So for example, right now, there is a downward gravitational force on me that pulls me towards the center of the Earth. There's another force that a lot of people don't think about, but it's pretty important, and it's the force from the ground pushing me upward. For most people, it's kind of strange to think that the ground, which is something inanimate, could be putting a force up on me. But let me try to convince you that the Earth really is pushing up on me by stepping on this toy here that's supported by a spring. As I step onto the spring, it contracts. So you can imagine the spring must be trying to expand out and put a force outwards. So that force, in effect, supports me, pushes up on my feet, and balances the gravitational force down so that I remain motionless. Now the ground is very similar to this spring. The ground is just a very stiff spring, but every time you step, you compress the ground a little bit, and that is enough to make the ground create a force on you, pushing you back up. And the force of the ground upwards must be equal to the gravitational force downwards so that you stay at rest. For simplicity, we draw all forces acting to the center of mass of an object. So even though the force is acting on my feet, I can draw that force upwards as acting through my center of mass. So there are really only two main forces on you. The force of gravity downwards and something we call the normal force, which pushes you back up. The reason we call it the normal force is because the word normal means perpendicular. And the force is perpendicular to the surface that you're standing on.
Okay, so good introduction there to free body diagrams. So let's look at the rules that we're going to follow when we write these diagrams. So the first step is to draw and label a dot that represents your object. So free body, we're not artists as physicists, so we use a dot or sometimes a box to represent our object. Then we want to start to plug in our forces. So we want to draw an arrow from the dot pointing in the direction of one of our forces that is acting on that object and label it with an arrow. So here we have the downward force. We have gravity, which is mass times, or force of gravity on us. So mass times gravity will get thus that force pulling downward. So a lot of times we would write F sub G for that one. Then we're going to repeat this same process for every force acting on our object, drawing the arrows roughly the same size if the force is the same size, or bigger or smaller depending on the size of the force. So here we can see our applied force, so maybe a push or something on this object, is a lot larger than these two forces that are equal but opposite one another. So once you've finished your free body diagram, you want to recheck to make sure you have everything drawn and labeled correctly. So every arrow needs to be labeled with the symbol for that force. And then we want to draw a separate arrow of our free body diagram to indicate the direction the object is accelerating in. So in this case, our overall larger force is our applied force to the right. So we would draw our overall acceleration for this object is going to be to the right. Okay, then we want to repeat the same process if we have another object we're going to draw a picture for. So let's try a couple examples. So we want to draw the free body diagram of a cat sitting on a chair. Okay, so we're going to represent our cat with a dot. We want to draw the forces acting on that cat. So obviously gravity is going to pull it downwards. So I'm going to label that force of gravity, so F sub G. And now my cat is not moving downwards, it's sitting on the chair, so there has to be a force that's equal pushing up on it. And we call that force, so any object sitting on a surface, we call that the normal force. Okay, and there's no other forces acting on our object. So that would be our free body diagram for a cat sitting on a chair. Let's try another one. So draw the free body diagram for a sled being pulled across an icy pond. So we're going to represent our sled as our dot. And again, gravity, our sled is not floating in air, so we're going to have gravity pulling it downwards. And it's not falling through the ice right now. So we have some force pushing upwards. We call that the normal force. They're equal, but opposite in direction, because our sled is not moving up or down. Now it doesn't tell us what direction the sled is being pulled, so I'm just going to assume to the right, but it could be to the left. And we're going to call that an applied force of you pulling on the sled. And then there's going to be some friction felt going backwards, but not maybe very much on the ice. So my arrow for friction is going to be a lot shorter. And now for this one, I'm going to have an overall acceleration to the right. Now I forgot to draw that on my cat picture. So for my cat was just sitting on a chair. So my overall acceleration for that one should have been 0, because the cat wasn't moving. All my arrows cancel out. Okay, so these are free body diagrams. You're going to try a couple more on your assignment for today.